Alrighty, kiddos, we're back and we're going to continue to talk about the Bohr model of the atom. If you remember, at the end of the last video, we talked about electrons being excited. And Bohr worked with the hydrogen atom. We told you why. Remember, it was the easiest of all atoms to work with when you're worrying about electrons, because it's only got one to worry about. So, if that electron's in its ground state, or in its lowest energy level, we say it's buzzing around in the first energy level. Now we can excite that electron. It can gain energy. And when it does that, it can move up by whole number increments to other energy levels. So it might go from the first to the second energy level. Or maybe from the first to the third. Or maybe it went from the second to the third energy level. Maybe it even went from the first to a fourth or even further energy level. All of those changes take energy. We're moving up. And when you move up, it consumes energy. Now, once again, keep in mind, these electrons need to go up by whole number increments. It's sort of like walking up stairs. You can go up 1 step, 2 steps, 3 steps. You can maybe even take 2 steps at a time. But you can never go up a step and a half or a step and 3/4. Likewise, when electrons fall down, they fall down in whole number increments as well. So, an electron might fall from the 4th energy level down to the 3rd energy level. When it does that, it gives off energy equal to the amount of energy that was required for it to move from the 3rd to the 4th. So it moves from the 4th to the 3rd. It gives off a particular wavelength of energy. Hey, if we know the wavelength of electromagnetic energy, can we find the energy of that electromagnetic wave? You bet we can. Remember, if we know wavelength, we can calculate the energy, so we can find the energy difference between the 4th and the 3rd energy level. Maybe that electron fell from the 3rd down to the 2nd energy level. That would also give off a different wavelength of light. And if we know that wavelength, we can find the energy difference between the 3rd and the 2nd energy level. Maybe it fell from the 4th all the way down to the 1st energy level. Wouldn't that give off a wavelength that's very, very short? So if the wavelength is shorter, that means the frequency is higher and the energy drop is bigger. Wouldn't that correspond then to different colors of light being emitted? Absolutely, and that's what Bohr surmised as well. Let's take a look back again at the emission spectrum for the hydrogen atom. Didn't we have some light being given off in the red? Yeah, that's a bigger wavelength. Must have been a low energy change. Didn't we have some light being given off in the blue and then in the purple and the violet? Yeah, those are smaller wavelengths, higher energy shifts. And that's exactly what Bohr predicted. So he calculated the energies that should have been given off by hydrogen as it moved from one energy level to another, and it ended up matching up exactly with hydrogen's spectrum. So that led us to helping to being able to understand the spectrum of other elements. Not completely, because remember, when you have one electron, the math is ugly enough. When you have 2 and 3 and 4 and 50, it becomes very, very difficult and crazy. However, the concept is that we're applying here is the same thing that allowed us to discover helium on the sun instead of here on planet Earth. Scientists were observing the visible spectrum being given off by sunlight, and they found a spectrum that they had never seen here before on Earth. It gave off something similar to hydrogen's, but in the yellow area. If we haven't seen it here on Earth, it's a new spectrum. That must mean it's a new element. We said it was named after the Greek god Helios and became known as the element helium. So the second most abundant element in the entire universe was discovered on the sun before it was discovered here on Earth. All right, a couple more pictures here to help describe this. Just sort of a recap and review. When an electron's in its lowest energy state, we call that the ground state. And when it moves up from that lowest energy state, we call that the excited state. Now keep in mind, these diagrams are not drawn to scale at all. Electrons are not nearly the size of the nucleus. They are really, really tiny, and they're huge distances away from the nucleus. So these illustrations, please keep in mind, they're not drawn to scale. Here's one that looks a bit more complicated. let's see, we can see electrons falling from really, really high energy levels to really, really low energy levels and everything in between. And we can calculate the energy that should be given off by that light when they make that shift, and sure enough, they match up with what we see when we actually analyze the spectrum. Now, to complicate things a little bit more, Bohr's explanation for the hydrogen atom, for hydrogen's observed spectral lines, was pretty good. However, the model failed to explain the spectrum of any other element. Moreover, Bohr's model did not fully account for the chemical behavior of atoms. In fact, although Bohr's ideas of quantized energy levels laid the groundwork for atomic models to come, later experiments demonstrated that the Bohr model was fundamentally incorrect. The movement of electrons in atoms are not completely understood even today. However, substantial evidence indicates that electrons do not move around the nucleus in nice, pretty circular orbitals. And that leads us to something called the quantum mechanical model of the atom, where we begin to treat electrons as waves instead of particles. And that's what we're going to be getting into in the next video. Now, before we do that, I thought I would work on one or two more problems for you related to wavelength, frequency, and energy of light. I think we need that practice. So, let's say that I have a wavelength of electromagnetic radiation that's equal to 388 nanometers. So it's on the violet end of the spectrum. Okay, really, really small wavelength as far as the visible spectrum is concerned. What is the energy of a photon of that electromagnetic radiation? So, see if you can do this. Pause the video right now. See if you can figure it out without my help, and then come back and see if you did it correctly. Alrighty? Good luck. Alright, welcome back. Did you use this equation? Energy is equal to hc over lambda? Yeah, we know the wavelength, don't we? We always know h because it's a constant. We always know c because it's a constant. We should be able to find the energy by using that equation. So let's see what we do. We take h times c and divide it by the wavelength. So h, if you remember, is 6.6262 times 10 to the negative 34th joule seconds per photon. Remember, we want to find the energy of one photon of that electromagnetic radiation, times the speed of light, which we know to three significant figures, 3.00 times 10 to the 8th meters per second. So seconds divide out there. We have the strange unit right now, so obviously we're not done. And divided by the wavelength, which was 388 nanometers. Now, some of you may have stopped right there and did the math, and you're going to be wrong. Take a look at your units. We end up with joules per photon here, but we have meters and nanometers over here. They won't cancel each other out. They're not the same unit, folks. So we need to fix this nanometer part of this equation. Let's get out of nanometers. So to get out of it, don't I put it opposite? And I want to get into meters so that meters will divide out. Now we have to know what a nanometer is. Remember, it's a billionth of a meter. So aren't there a billion of them in 1 meter? So now nanometers divide out, and meters divide out, and we're in the unit that we need to be in, which is joules per photon. That's what I asked about. So let's plug this in and see what we get. Okay, kiddos? So 6.6262 second EE to the negative 34th times 3 second EE to the 8th divided by, what was my wavelength? 388. And I want to multiply that by 10 to the 9th times 10 caret key 9. All right, let's see what we end up with here. To three significant figures, 5.12 times 10 to the negative 19th joules per photon. So that sounds fairly reasonable. 5.12 times 10 to the negative 19th joules per photon. Let's see. Yep, that's a very, very small amount of energy, and that would be expected because a photon, especially according to physics, physicists are massless particles, so an individual photon does not carry a whole lot of energy. Okay? All right, should we try another one since we have time? Yeah, let's try one more just for fun. We'll clear this off. Let's try, how about this? What if I give you the frequency of some electromagnetic radiation? Let's make it 4.07 times 10 to the 15th seconds to the negative first. Remember, that's 1 over seconds, or cycles per second, or hertz. What would the energy be for 1 mole of these photons? Yeah, try that one. Go ahead and pause it, try the problem, and come back and see how you do. All right, welcome back. Did you start with this equation, E equals h times the frequency? I hope you did, because we always know h, and I gave you the frequency. Now the problem with that is that will give us the energy for 1 photon. We'll need to add one more step to find the energy for a mole of those photons, okay? So let's take h, 6.6262 times 10 to the negative 34th joule seconds per photon, times the frequency, 4.07 times 10 to the 15th seconds to the negative first is the same as 1 over seconds. So notice seconds divide out. So we know I have joules per photon, but we want to get out of photons and get into moles, right? So 1 mole has how many photons in it? That's right, Avogadro's number, 6.022 times 10 to the 23rd. So now we're going to get joules per mole of photons, which is what I wanted to know. Joules per mole. So let's plug this in, see what we get, kiddos. 6.6262 second EE to the negative 34th times 4.07 second EE to the 15th. Yep. And we're going to multiply that by Avogadro's number, 6.022 second EE to the 23rd, and it looks like we get, oh boy, that's an interesting number. We're allowed 3 sig figs, 1.62 times 10 to the 3, looks like it's 6th joules per mole. 1.62 times 10 to the 6th joules per mole. All right, just a little bit of extra practice for you. Hope you liked it. Talk to you later. The next video is going to be on the quantum mechanical model of the atom. Please bring your thinking caps with you then. Alrighty, bye-bye.